TanStack DB is an exciting local-first state management library. And Electric SQL has been popularizing sync APIs with durable streams and their namesake Postgres replication project. Together, they enable complex, snappy multiplayer user experiences. My name is Christian, and I'm a polyglot engineer with a fondness for Elixir. In this two-part series, I'll walk through a realistic project, starting with a local-only front end. This part can run without Elixir if you're only interested in the front-end side of things. Then we'll add a backend that lets the app work for multiple users, enforcing business logic and keeping everything in sync. Now, I'm not a fan of writing to-do list apps to show off libraries. If you've been watching Code and Stuff for a while, you probably already knew that. I don't know about you, but I think it's hard for people to decide where to eat together. Some groups have someone who makes the decision for them, but what if we did something a bit more democratic? The Food Captain app allows a group to gather ideas for restaurants, synchronizing the available options across everyone's browsers as they're created. It implements ranked choice voting, making sure that a true majority of voters are open to the final decision. A winner is revealed with each round of elimination available for the curious or skeptical. This local-first app combines optimistic updates with server-side logic and synchronization. And by the end of this, I hope you'll understand how it was built and feel prepared to consider this tech in your own projects. As always, the code is available on GitHub with a link in the description. Check out the starter branch if you're following along. Let's get into it. Like I mentioned, TanStack DB is a client-first state management library, and it kind of feels like working with a database. Application code gets its data through live queries, which read from collections. Collections can be filtered, sorted, and joined. They also have support for mutations like insert, update, and delete. Whenever you mutate the state of an item in the collection, that change gets applied to all of the subscribers to the collection. But this kind of thing can be done by any local state management library. The important part is integrating this with a backend. TanStack DB supports a few types of collections, which fetch and persist data. If you're already using TanStack Query, the query collection might serve as a great on-ramp to DB. In our case, we'll prototype with the localStorage adapter. This has just enough separation for us to consider what's optimistic and what's persisted without getting caught up in API design just yet. We can stage changes with optimistic writes, which are immediately presented in collections and their subscribed views. When the front end is satisfied with local changes, it can commit transactions and send those mutations out. The response is then confirmed by the adapter and is finalized in the collection. If another browser tab updates that data, those changes will be merged into the collection and update the UI. This forms two loops, the local optimistic data loop and the external synchronized data loop. And if there's ever a failure in committing a transaction, which isn't likely with local storage, TanStack DB rolls back modifications automatically. Your state ends up matching whatever the backend has available. Now, that was a lot of preamble, so let's move on to the code. If you freshly checked out the starter branch, follow these instructions to get a server running. You can also take the code and run it on whatever server you want. It's local first after all. Opening up the app, there are two hard-coded sessions available. This takes place in sessions.tsx, which is mounted at the root of /app. But hard coding is no fun. Let's create our first TanStack DB collection over in collections.ts. The create collection function defines that database-like layer from the diagram. Local storage collection options is the constructor that actually indicates, for now, that we're using the local storage adapter as opposed to React Query, Electric, or something else. It requires a storage key argument. What are we calling the local storage property? And all collections, regardless of their type, have a getKey function, which extracts the primary key for each object. This gets used in update and delete operations, as well as when we're synchronizing objects. Session is currently typed as any, which is far from ideal. Luckily, TanStack DB supports schemas through any standard schema library. In this case, I used Zod over in schemas.ts to define our core data schemas. So we'll grab session schema and set that to be the schema of our collection. So we'll say schema is session schema, and of course, that's going to be coming from schemas. Now we can get rid of this any, and the cool part is TanStack DB is going to be using that schema and its derived type throughout our application. Now we know that ID is a string, and so on. This schema is also used to validate inserts and updates, which will prevent us from creating a session without a name, for example. TanStack DB supports React, Vue, Solid, Svelte, and even Vanilla.js. But in React, we're going to use the useLiveQuery hook. This is what connects the UI to collections, and anytime the collection changes, the query automatically reruns. So we'll use that in our sessions route. useLiveQuery, and this is going to take a query builder callback. So we've got Q, and Q has stuff like a from method. And we can say that we want session to be the result of our sessions collection. It looks like my import got a little weird here. Now with this from, we can also chain on other methods like where, join, and order by. In fact, let's do an order by and take the session. And we want session dot inserted at, let's go descending, so we'll have the newest ones at the top. Now this is going to return an object which has keys like data, which will map over to sessions. Means that we don't need hard coding anymore. And we're also going to have is loading, is error, and status all defined here. Perfect. Actually, while we're here, let's filter these where session has a user ID of whatever the current user's ID is. I have a utility function for that. Not important. This might be how you initially try and build it, but there's actually query methods that are exposed by the library that allow all of the reactivity to work. So instead of a triple equals that you might normally use in a front-end app, we're going to use the EQ method exported from TanStack DB, and it takes two options, and that'll work and actually properly reconcile. So now we're grabbing all sessions that were created by the current user and sorting them by their inserted at with the newest at the top. And now if we head over to the app, we'll see a lovely empty state. But we should be able to create our own sessions. For this, I'll define a function called handleCreateSession over in this sessions route component. So let me grab this example and we can walk through it. In this function, we're going to take in a name, and we're going to insert that name into the sessions collection as a full session object that has all of the fields that would pass validation. In fact, if I remove one of them, the type system will complain saying, that's not a session. So we'll add that state back and start it in an open state. And we can pass this function down into our sessions list component, which was waiting for it. So onCreateSession is this handleCreateSession function. Then a new button will show up in the UI, allowing us to open a modal and create a session. Operations applied directly to collections are automatically committed to the backend. So if I create a new session, let's call it lunch, and hit save, it'll show up on the list. And when I refresh the page, it'll still be there. Now, if I open up another page and add a new session, let's call it dinner, naturally, it'll get appended to both tabs and keep them in sync. With a more powerful adapter, this could also be shared around the world. But if we click on the session to load its details view, we get a not found. And that's because the session details view isn't using our collection yet. Let's go fix that. So over in session details, index, we can see that we're just hard coding a null session, just like before. So let's import our collection. Then use liveQuery. And inside of this query, we're going to do q.from. Session is our session collection. And we want to look where, given a session, there's an equality between the session.id and the session ID that was passed in through our URL. This normally will return an array, but we can do a find one to force this to either be an object or null. Now, being a React hook and reading a value from another React hook, there is a requirement for a dependency array. Just like any other React hook, you just add it at the end, saying, I want this to reevaluate when session ID changes, because session ID comes from another hook. This is just the way that React apps do it. And now we can map data to session, and I'll save you the typing here. We'll grab all of those other properties and finally remove the hard coding. And I need a little equal sign. There we go. Now, if I take a look at session, it has all of the properties from a single session rather than being an array, because the type system knows what's going on. And if I go over to the page, click on lunch, we can see the name lunch and the fact that it has an open state. So let's move on to creating restaurant options. I have an idea for a slightly different user experience for options where we can have a few in progress and save or edit them inline. But first, let's create a collection for options, giving it a storage key and a schema. This should be pretty boring and predictable by now. Over in collections, we'll define this, and let's add the schema. That is it. Now, our session details view ends up conditionally loading options management or the voting interface. And I know that these could be subroutes. This is just the way that I built the demo. But if we go into options management, we can see that we have a placeholder on add option, and we've got our characteristic empty array as a placeholder for the options. So let's do what we do and import options collection from collections. Then load this data with a live query. We're going to grab from options collection where the session ID is the session ID, and we'll do our sorting and our dependency array. And just like sessions, we'll add an insert, which will create a option with the name new option on our session with the right dates. And if it fails for some reason, we'll add a toast to the application. If I head over to the app, I can click add first restaurant and the new option shows up. But unlike sessions, let's support updates of the name property. So we're going to add a callback for when we want to save an option that takes an option ID and a name. Then in the implementation, we call options collection.update, taking that option ID, which we defined as the key earlier, and then anything that we do to this draft object, we will end up persisting to our database. So I can do things like, set the name to that name. We can change the updated at. Any of those modifications will end up sticking in the database. Just don't change the key. This returns a transaction, which we can wait for. And when it finishes, then this function will return. So let's wire this callback into our component for the option cards. We'll call this onSave. Let's actually take a look at the option card implementation for a moment. So an option card keeps track of whether it is editing, what the name is temporarily if we are editing, and whether we are saving or not. So let's go over to our app, click on this new option, and let's call it newer option. We'll hit save, and it gets persisted. When I refresh the page, it's still there. And if I go into a multi-tab view, I can add an E here. Whatever I want to do, it ends up getting persisted across everything that's subscribed to that same local storage key. If this card had a more complex state or experience, you might want to use a form library, but in this case, it's just a single string and a Boolean. But all of this has me thinking, wouldn't it be nice if new options showed up as cards that are already in an edit state rather than just creating one that says new option? That would let us think up ideas and edit them locally before sharing them with others. But when we call insert on a collection, the change is automatically persisted. And that's where manual transactions come in. Transactions are a container of operations that are optimistically stored in memory in our app and get committed or rolled back together. And we can wrap an insert in a transaction to get what we're looking for. Then we can make whatever changes we want to that card before it gets persisted and propagated. We can even have more than one transaction going on at once, but I'm getting ahead of myself. There's no rule about where transactions are created, but I found that it's helpful to create them in a file that I'm calling mutations.ts. In here, I'll import the create transaction function from the database package, along with the options collection we recently created. But the most important part is that I'm specifying auto commit false. Now, if we follow the red squiggle, this is missing something. In this case, it's a mutation function. We haven't encountered these yet since they're usually defined by default in the local storage adapter. But since we're taking the transactions into our own hands, we're going to have to handle this mutation concept. Basically, this is a function that's called to actually commit the changes. It's where you'd call an API, for instance. If this function throws an error, the state changes get reverted. And if it returns successfully, changes are persisted. So let's drop in a mutation function and break down what it's doing. In the case of the local storage adapter, we confirm the changes using a utility method called acceptMutations, which takes a transaction object and applies the changes. We'll look deeper into the transaction object and the mutations it contains in part 2 when we end up converting it to an API call. But for now, this is all that we need to do. And now in optionsmanagement.tsx, let's start playing around with transactions. We'll start by importing the create session option transaction function that we just wrote. And we need a place to store the pending transactions with up to 1 per option. I'm going to use a ref since this isn't directly responsible for triggering renders in React. So we'll have a ref, which I need to import, that maps from string to transaction, defaulting to a new map. We can use this anywhere in this function without triggering a re-render. So when we create an option, instead of just inserting it into the collection, we'll run it in a transaction, storing that transaction reference in this map. Running a mutation in a transaction is actually pretty simple. So I'm going to replace onAddOption with its transaction counterpart, and let's walk through it. Here we're going to create a transaction, and then whatever we do inside of this mutate callback is going to be a part of the transaction. So we grabbed our insert from before and just nested it into a mutate callback. Then we set this as the pending transaction on this specific option. Now, conveniently, when the name of a restaurant option is an empty string, the card component automatically enters edit mode. It's like I planned for this or something. So I'll head over to the component and add restaurant. And now we have a new restaurant that shows up here, but let's go into side by side. If I create a new restaurant, it's not going to show up anywhere else yet. Because we're using transactions, we're going to have to handle the commit and rollback behaviors. So let's go to the save function. And instead of just always running an update directly, let's do something a little different. If we're already in a transaction for that option, let's do one more update to give it that new name, the one that we want to save instead of the empty string, and then wait to commit that transaction. Then we can remove the pending transaction from our ref because we no longer need it. It's already committed. Otherwise, we'll fall back to our old behavior of just directly applying an update, which will commit automatically, and we wait for that promise. Now, if I go into the UI, add a restaurant, and we're going to call it new restaurant and hit save, it gets synchronized and persisted whenever I save because the transaction gets committed. Now, one more thing, what if we want to cancel? In this case, canceling is going to keep a restaurant with a null name here and close the card. And if I refresh the page, that's not quite right. Instead, we should remove that inserted restaurant. So we'll add a cancel function, which is going to look up the transaction for the option. And if there is a transaction, we'll roll it back. So let's pass that into our option card on cancel option. And now if I start creating an option and then bail on it, it'll get removed. Now, technically, when we create an option and then save it, we are performing 2 operations, an insert and an update inside of a transaction on the same exact object. TanStack DB automatically merges these operations into an insert behind the scenes. It's not a big deal for the local storage backend, but it's a great optimization once we add a server. Being able to combine in-memory and remote state in a single place without too much special case code is what got me excited about this library in the first place. If you're going to be shoving a ton of values into TanStack Query or introducing separate local state containers and context providers, you might benefit from DB. There's also no rule that an application has to use the same state provider for every single collection. There's even a local-only collection that can be used where it doesn't persist anywhere. You could probably use this for complex form state if you were interested. For demo purposes, I wanted to add a button that creates a few restaurants. I'll just paste this in, and it's not really anything to look at too closely. But we have a list of restaurants and create a transaction, performing a bunch of inserts, and finally committing it. I mainly did this in a transaction because the infrastructure was there to begin with. So instead of add first restaurant being the only option in the empty state, we'll also have this demo button. Now, if I go into an empty session, I can click add demo restaurants, and they all get committed at once. They're also all editable, obviously, and they all get committed in the background. With our options in place, it's time for the last step. We're going to take that local state to the next level with the final collection, which is votes. Votes is going to start out as a pretty boring collection, which is going to represent a user's private ranked votes on options within a session. Naturally, we're going to go over to collections, create one more, and this one's going to take in the session vote schema and be stored under the key votes. We're going to be using transactions, so I'm going to go over to mutations and have a new function, and this one is going to take in votes collection when doing the mutation commitment. And with that in place, let's take a look at our voting interface. Now, this component is going to be a lot more complicated than the other ones, and I actually extracted a lot of the core logic out of the component and into a hook. That hook is going to provide the options that have been ranked, the options that are available for ranking, a boolean of whether we're loading, and then a handful of utilities like adding an option, removing one, moving them up and down, clearing their votes, and saving the votes in the end. And the rest of this is pretty boring. We'll loop through the options and render them with buttons wired up to those utilities. In the starter branch, all of the actions actually do nothing. I'll open up use voting, which is in hooks voting.ts, and notice that it doesn't do anything. So I'll paste in the final implementation to show how it all comes together, and we'll walk through it step by step. Right off the bat, we've got a reference to a transaction. If we've done any edits, they'll be stored there. Then we list out all of the options, filtering to the session that we have open. Now this is our first join. It's a left join that will add a corresponding vote object to the returned option data if there is a vote that matches that option. Finally, we sort these potentially voted on options by their rank. But notice the question mark after vote. This is because vote is known to potentially be undefined. TanStack DB is smart enough to know that a left join might result in an undefined value on the right side. So in this case, option is present, but vote might not be. Then we'll split out the options into the ranked and just simply available ones. We'll return those later. And originally I tried to write this as two separate queries, but it got tricky to articulate do a join, but only return where the join fails using TanStack DB. It might be possible, I just couldn't figure it out. And now for the utilities. Adding an option is pretty simple. Grab the next rank in the sequence, putting it in a transaction that's either already happening or that's created on the fly. Then insert, just like we did before. I'm using a deterministic ID here defensively, so the code might blow up if the UI using this hook manages to create two votes for the same option. Since the ID is the key, the database will understand that two inserts on the same key is not okay. Move up is next. We find where the option is, look at the one before it, and then assign their ranks to each other using two updates in a mutate callback. The objects current and above are different from the vote drafts in the update callback, so we can safely read their values without worrying about stepping on our own toes. They're not the same objects, they just represent the same concepts. So when we set the rank on one and then set the other rank to the other, everything should work out nicely. Move down is the same thing, just in reverse. We're looking at the option below it, and we're guarding for whether this is the last option. And finally, when we remove an option, we need to ripple edits to all of the ranks of options that come after it. So in the mutation, we run a delete on the removed item, and then for every other option, we're going to use the minus equal operator to remove one from the rank, shifting all of those up. I didn't quite realize that you could use minus equals on these drafts, but it worked out just fine. Now, clear is going to go through all of the ranked options and just delete their votes, removing the reference for the transaction because it's no longer in flight, and committing. And the most easy one, when we want to submit the votes, we grab the transaction, clear its reference, and commit. And that's pretty much it. So over in the app, let's open up dinner and go to the voting page. We can add options one by one and they rank up. We can save them and they'll show up on the other side. We can also move them around. Let's say that we want to move Burger Barn down and we want to remove Pizza Palace and let's add Sushi Spot. We can do all of those mutations, hit save, and it'll be persisted and propagated over to the other tab. If I clear them from one tab, they'll clear from the other, and that automatically saves, just like we'd expect. But start adding them up one by one, and they don't sync up until I save. Testers out there might wonder what happens when these things get out of sync. Let me show you a funny situation I ran into during testing. So I'm going to insert these, and then on one side, I'm going to re-rank this, and on the other side, I'm going to add another option and delete this one. If I save this, I now have second choice, third choice over here, and technically it would let me save that. This is where a validating backend would really come in handy, rejecting bad writes instead of corrupting our very important meal decision. And we'll get into that in part 2. But that sums up the front end portion of our implementation. We've come a long way, setting up state management patterns that let us create, read, update, and delete objects with clear ways of staging those changes locally. This could have totally been built without TanStack DB, but in my opinion, it would have been quite a bit more difficult to work with. Hopefully you learned a lot from this project and stick around for part 2 where we'll make this multiplayer. It's not actually as much work as I had expected, and it'll be made even easier as these very early libraries mature. But for now, this has been Code and Stuff. Thanks for watching.